Nuclear fusion is a very rich source of energy, so much so that the stars get their power from it. And if it can be replicated on Earth, it has the potential to provide nearly limitless energy with zero carbon emissions. Unlike nuclear fission, which is used to power today's nuclear plants, fusion does not produce long-term radioactive waste. Ever since the turn of the century, the technology has seemed just beyond reach. Yet, given the significant potential payoff, billions of dollars continue to be invested in this sector. And now a world with almost unlimited access to renewable energy is one step closer to becoming a reality. So what is this new reactor? Can it provide our world with unlimited energy? And how does it fare against the already available reactors? Powering the sun and other stars is the nuclear fusion reaction, which has always been considered one of the most difficult energies to harness, yet the most efficient on all fronts. To put it into perspective, the power to harness nuclear fusion energy is a bigger discovery than the invention of the telephone and the light bulb combined. Two light nuclei combine to produce one heavy nucleus during a fusion process, if scientists can figure out how to use it in Earth-based machinery. Germany, the hub of engineering, has pulled it off again by creating a new nuclear fusion reactor in Germany's plasma research facility. Having the power of the sun inside a facility is different from the more common nuclear fission reaction. This incredible one-of-a-kind device that can produce clean energy that can power our entire Earth for countless years is named the Wendelstein 7X Stellarator. The temperature at the core of our sun is around 15 million degrees, but this reactor operates at a temperature of 100 million degrees. This reactor basically ends up creating a live miniature star inside of it with properties similar to our sun, and is able to sustain this huge amount of energy in a stable form for a long duration of time. So how does this seemingly impossible technology work? As a reference, the sun's surface only has a temperature of 5,505 degrees Celsius. Contrary to conventional nuclear energy, which is produced when large atoms smash together, fusion energy is produced when atoms fuse together. The radiation problems caused by atom-splitting power are not present with this energy source, with the exception of the radioactive panels that cover the reactor's inside walls. Fusion is the most environmentally friendly way to generate power. We need a certain sort of equipment to give atoms a 100 million degree blast that will ignite them. One of the two of them making a difference right now is W7X. The electromagnetic fields created by plasma are used by devices like MIT's alkylator CMOD Tokamak to keep the charged particles under control. Fuel injection produces a hot, very energetic cloud of particles. Power generation is, however, just a brief operation due to instability issues. Stellarators like the W7X employ banks of magnetic coils to confine the plasma, giving them greater control and enabling the hot ring of helium jelly to inflate for prolonged periods of time, even if they don't quite match the output of the Tokamak. The W7X gadget, which is 15 meters wide, seems to have shown how to solve that issue. The ITER nuclear reactor, the first and largest unit of its sort ever made by a French nuclear power research center at Cadarache, is another advancement in nuclear fusion that has gained recognition. The gadget would create 500 megawatts of electricity, which is 10 times the energy it would need to run, by fusing two different types of hydrogen, known as deuterium and tritium. When ITER begins operating in 2025, it will be a completely new kind of nuclear fusion device with a 100-foot height and diameter. In that it suspends hydrogen plasma that has been heated to the pressures and temperatures required to fuse the material into helium, a stellarator works similarly to a tokamak. The Wendelstein 7X is made up of 50 3.5-meter-tall superconductive magnetic coils. As contrasted to the torus or donut-shaped design of a tokamak, the stellarator confines the plasma in a twisting and swirling pattern. The movement of the electrons and ions in a tokamak is made to mimic an electric current flowing through a transformer. This current produces a vertical looping magnetic field that generates the required spiraling field lines when coupled with a magnetic field that already covers the whole length of the tube. The tokamak, on the other hand, can hold more plasma. This is partly because a tokamak symmetry allows particles to move along smoother routes. Due to the various wiggles and ripples they encounter, stellarators frequently lose large amounts of tiny particles. Because of this, the great majority of fusion studies carried out since the 1970s have resulted in the massive ITER reactor project. Thanks to the insertion of graphite tiles within the Wendelstein 7X's wall, warmer temperatures are now possible. In order to exert greater control, the operators may pump more plasma in at higher temperatures and shield the swaying chamber walls with an internal liner called a diverter. The magnetic field that keeps the hot plasma controlled and removed from the vessel's walls was designed with a great deal of computational and theoretical effort to address the shortcomings of previous Stellarators. The Wendelstein 7X Stellarator was improved to demonstrate the viability of power facilities powered by Stellarator-style fusion reactors. One of the key objectives was to minimize the energy losses of the plasma due to the ripple of the magnetic field. Even after being anchored to the magnetic field lines, plasma particles may still drift away, losing energy in the process. In contrast, because of its symmetrical shape, minute plasma vortex movements and turbulence, which is also considered a loss channel, the Tokamak experiences negligible loss from magnetic field ripple. These energy losses are impacted by Stellarators. As a result, Stellarator development must reduce neoclassical losses to meet Tokamak's superior confinement properties. The magnetic field of Wendelstein 7X was intended to reduce the losses as a consequence. Wendelstein 7X can now create high-temperature plasmas and set a record for attaining high temperatures using the heat technology that is currently available. It can be shown that by combining temperature, plasma, density, and energy containment time, one may come very close to the specifications for a burning plasma. While turbulence losses were negligible at these high plasma temperatures, neoclassical losses, which accounted for 30% of the heating power, considerably contributed to the energy balance. A thorough experiment has now shown the operation of Wendelstein 7X neoclassical optimization. The same plasma amounts and profiles that contributed to the record performance of Wendelstein 7X were expected to be achieved with implants with a less ideal magnetic field. The result was clear after estimating the projected neoclassical losses. They couldn't possibly be more than the heating power being used, physically speaking. As a consequence, the plasma properties seen in Wendelstein 7X can only be produced by magnetic fields with negligible neoclassical loss. The opposite is also true. By altering the Wendelstein magnetic fields, neoclassical losses might be significantly reduced. Tokamak, in comparison, has significant drawbacks. A transformer's meager capacity to swiftly pump a current across plasma is inadequate for a commercial fusion reactor. Occasionally, the plasma current may unexpectedly fail, leading to disruptions, which are rapid losses of plasma confinement that can release magnetic forces strong enough to damage the reactor. The same issues plague even more contemporary designs, like this spherical Tokamak. It is not necessary for the fields created by the external coils to be pulsed, since Stellarators do not have any plasma currently flowing through them. Some teams have stuck with the concept because of these two features. The energy generated by the reactor is practically pure since it doesn't create heat via nuclear fission in a controlled nuclear process. Despite the Wendelstein 7X's incapacity to create energy on its own, it nonetheless serves as a first step for us in developing a Stellarator reactor that would eventually produce limitless energy utilizing a mechanism similar to that which drives the sun. Keep watching our videos to discover more about the most recent updates and the direction that technology is taking.